Hi everyone, I hope you can hear me. Can you please confirm? Okay, so let's just get started. So today we are going to discuss some of the problems in the synchronization, and specifically we are going to discuss related to semaphores, right? So let's just get started. Now, in this like in the yesterday session, we have seen a few of the problems related to mutual exclusion, related to progress, related to bounded weighting, and we have explained clearly like what is the difference between progress, bounded weighting, and all, right? Okay. So now today we will move our focus to the semaphores. Now let me just start with the semaphores. Okay. So generally, we have two type of semaphore. One is called counting semaphore, and another one is called binary semaphore. Counting semaphore are the semaphore which can count the values, which means which can do two things, which can provide you the security, which means like you can determine that okay, at a time these many number of processes can enter in the critical section, something like that, right? I mean, sometimes it is desirable to let multiple processor also enter in the critical section, right? So counting semaphore does the same thing, and binary semaphore provides the mutual exclusion also, and the like I mean it is a solution to the synchronization. So basically like both are providing the synchronization solution, but the counting semaphore is also allowing you to have more than one process at a time, right? And similarly, I have a mutex. Mutex is just one idea which is saying that you should be providing the mutual exclusion using some programming, which means like you do not always have to use some hardware support. Using some programming only, you should be able to provide some mutual exclusion solution, right? So that's what this says. Let me know if my voice and everything is clear, right? So yeah, okay. So let's just move further. So let's just see some of the problems in the in the semaphore, which is binary semaphore, and the counting semaphore also. Now, if I ask you that, can you just tell me that how does the binary semaphore look like? Okay, which means implementation of binary semaphore. Then let's just ask this question and solve this question. That how do we implement the binary semaphore, right? Implementation of binary semaphores. So basically, there are of two methods that we use in binary or counting semaphore, which is called P and V, right? Or wait or signal. So we call it wait. We call this signal. Since the binary semaphore can have value which is 0 and 1 only, so that is why here, I mean, if it is signal, you will just set the semaphore value to 1, which means like irrespective of the old value, you can just set to 1 because it is binary semaphore. Signal means like make it 1, wait means make it 0, right? Wait means make it 0. And what if it is already 0? It means it should wait. So basically, you can have like while something like this. I think I have on the next page. While s equal 0, then you can say that okay, let's just wait it for some point in time. If it is already 0, then let it wait. If it is not 0, if it is 1, then make it 0. So that's what the implementation says. Let me know if that is clear to everyone, right? Okay. So now let's just move to these are the two semaphores that I have, binary counting semaphore. Now let's just move to the counting semaphore. How does the implementation of counting semaphore looks like? So what do you think? How does the implementation of counting semaphore should look like? So this is the implementation of binary semaphore. Now if I just go to the implementation of counting semaphore, right? Implementation of, instead of binary, if I say it is a counting semaphore. Now here in this case, since you can have value more than one, I mean not just 0 and 1, you can have values which are 0, 1, 2, 3, something like this, right? So you can have value starting from 0. So that is why if it is signal, you will say okay, let me just do plus plus, right? Let me just increment this value. But in case of wait, you will say if it is already 0, right? I mean, if it is not 0, which means if it is some positive value, you can directly decrement. But if it is already 0, then you will say okay, let's just wait it. Let's just wait for some time, which means while s equal 0, or maybe less than equal to 0, whatever you want to say, right? Equal 0 is also fine, which means if it is already 0, you just wait for some time. If it is not 0, then you just decrement it. That's what counting semaphore says, right? So I hope the implementation of binary semaphore and the counting semaphore is clear to everyone. That how does the binary semaphore look like and how does the counting semaphore look like. Cool. So if you see the implementation of binary semaphore then or counting semaphore, currently whatever the implementation we are having, it is called busy wait implementation, which means that you are waiting in the for loop, right? So that's called busy wait implementation. Now tell me, are you consuming CPU cycles? If you are in this while loop or for loop, are you consuming cycles? Then obviously you are consuming cycles, right? I mean, CPU has to execute it again and again. So can you tell me, if you are executing this particular statement, then at that time, where is this process, in which queue the process is? Is it in the ready queue? It is in the block queue? It is in the running queue? In which queue it is? It is obviously in the running queue. So basically you are running this program and then that's why you are stuck in the loop. So is this a good idea to keep the program in the running queue and don't do anything? I mean, it is not doing anything, right? So it is just in the loop. So obviously it is not a good idea. So that is why you can have another implementation that is called a queue implementation. Okay. So generally we will be having that implementation only. I mean, you can have this implementation, that implementation. For most of the problem, it won't matter. But like generally, if I'm saying semaphore, then it means that you are having queue implementation by default. Okay. So uh, yeah, let's just see. So this is the implementation that we have, which is again a blocking implementation or the busy wait implementation, and this implementation is for the counting semaphore, right? I hope everyone can write this easy code, right? That's very easy code. Like if it is signal, then you can directly increment, but if it is wait, then you can just wait itself means wait, right? You can just wait. So here you will be having a while loop. Okay, so let's move further. Please let me know if this is clear to everyone, right? Now let's move further. Now this is the implementation that we have, and this implementation that I have copied from the Galvin. So this implementation, let me just drag this implementation a little bit. So this implementation is basically for the like counting semaphore, and this implementation is using the queues. So let me just show you that how does this implementation look like and what it is saying. See, it is saying this is semaphore implementation. Just look at this wait and signal. Maybe I can copy this on the next slide, and then you can see, right? So this is a queue implementation where I do not run in the for or while loop forever. I basically, if I want to wait, then I can wait outside the running queue. That's what it says, right? If I want to wait, then I can wait outside the running queue. So it is saying that in case of wait, if you want to wait, then add that process to the list of the block process, right? So instead of making it looping forever, then you can add that process to the list of blocking process. So that's what is the only difference. And similarly, whenever you are doing signal, at that time, what you can do, you can say that okay, if it is already blocked, you just increment it. If it is already blocked, then just remove one of the process from the blocking process, right? I hope that is fine to everyone. So anyway, like it is not very much concerning that which implementation you are using. I mean, that is fine to us. Okay. I mean, if for the simplicity, if you want, you can just keep the very simple implementation. Otherwise, like it is like another implementation is saying, instead of looping in this while loop forever, instead of doing the busy wait, let's just do something which is moving the process in the block queue. And whenever you are doing signal, then just check that if there is a process in the block queue, then you just remove that process and increment this plus plus, right? Okay. Now let's solve this problem. What this problem is saying, at a particular time of computation, the value of a counting semaphore is 7. Then 20p operations and 15v operations were computed on the semaphore. The resulting value of the semaphore will be. So it was 7. Then 20p means you must have decremented 20 times. 15v means you must have incremented it 15 times, right? So this is the final value, which is 7 minus 5, which is 2, right? So B should be the correct answer. Very easy question. It is just saying that how many times you are incrementing and decrementing. Based on that, this question is asking something, right? Okay. See, answer is 2. Now let's move to this question. Again the same question. A counting semaphore was initialized to 10 and 6p and 4b. So 6p, which means minus 6, plus 4b, which means plus 4. It means it is minus 2. That's why the answer is 8. Very geo question, right? Yes. Now let's move to the next question. What this question is saying, a solution to dining philosopher problem which avoids deadlock is to ensure that philosopher pick up the left fork before the right fork. So basically, I want to have a dining philosopher solution, and where I do not want to have deadlock, obviously. So do you remember what is the dining philosopher problem? It says that there are philosophers which either think or they eat. So let's suppose this is the fork they have, and this is another philosopher, right? Let's suppose this is another philosopher, this is another fork that they have, this is another philosopher, this is another fork they have, this is another philosopher, another fork, and then another philosopher, another fork, right? So basically, there are how many forks? There are 1, 2, 3, 4, 5 forks, and then there are how many philosophers? 1, 2, 3, 4, 5. So every philosopher either think or eat, right? Either think or eat. Now here everyone is either thinking or eating. So now if they want to eat, then they are saying that they need both the forks, right? I mean, this will be needing this left fork and right fork, both the forks. Now suppose if I say that you first pick if I say to everyone, then first pick the right fork, okay? So it will pick the right fork, 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 it will pick the right fork. Then I will say, okay, now pick the left forks. So this will say that, okay, left fork is occupied. This will, everyone will say that left fork is occupied, right? Yes. So in this case, what's going to happen? If everyone is saying that left fork is occupied, then in this case, what will happen? There will be a deadlock. Can anyone tell me why there is a deadlock? Because there is this condition is called circular wait or hold and wait. This is holding something and waiting for something else, right? So this is called circular wait and hold and wait. Now, can anyone tell me what could be the criteria by which there is no deadlock? I mean, there are two more conditions which are mutual exclusion, and there is one more condition. Can anyone tell me for the deadlock? Mutual exclusion, circular wait, hold and wait, and what is the last condition that we have? Anyone? So there are four conditions for the deadlock. Okay, so I mean, if you want to prevent the deadlock, then what you need to do? You need to basically just violate one of the condition, right? So you can just violate one of the condition. Now since okay, the last one is no preemption, right? So no preemption. Now, if you want to avoid the deadlock, then you can just violate one of the conditions. Since all of these conditions are satisfied here, why? Because there is a circular wait. This is holding, everyone is holding and waiting for something. Hold and wait is there, circular wait is there. No preemption means that it does not want to leave this. I mean, this is a resource, and preemption of the resource basically, right? This resource cannot be preempted. I'm not saying that okay, it is not letting it go, right? It cannot be preempted. It cannot leave this particular process. So philosophers are the process, and the forks are the resource. This is a process, right? So no preemption means that you cannot leave this resource cannot be preempted. And mutual exclusion obviously is there because a fork can be assigned to only one process or one philosopher, right? So all of these conditions are satisfied, but that's why there is a deadlock. But we like to avoid the deadlock, what we do, we generally have one of the condition violation, right? A violation of the one of the condition. Since the mutual exclusion is not easy to easy to nullify, reason being is that you cannot share the fork. If you can share the fork, then yeah, mutual exclusion is not there, then everything is fine. But since you cannot share the fork, that's why you cannot nullify it. No preemption also you cannot nullify. It means that okay, let this philosopher, I mean this philosopher, let's suppose one, this philosopher is saying that okay, let me just give away my resource, let this resource be preempted, and then it can assign to another one, right? So no preemption is also not easy. But yes, this circular wait and hold and wait, we can violate these conditions. How? What we will do, we will allow asymmetry in this case, right? This is the solution to dynamic philosopher problem, which is saying we will allow asymmetry. Asymmetry means that instead of this symmetry, this is a symmetric condition, which means everyone is picking the left one and then they are going for the right one, right? That's why this is a symmetric condition. So what we will do, we will just allow asymmetry, and here I will say that okay, let just do one thing, let one of the philosopher choose the right one, right? I mean, one of the philosophers. So what we will do, we will say to everyone, maybe to everyone we will say okay, left, 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 okay, and then to one of the philosopher we will say you don't pick left, you pick the right one first, right? So let's suppose that I'm saying everyone I'm saying that okay, you pick left, you pick left, you pick left, you pick left, and to this philosopher I'm saying you don't pick left, you pick the right one first, right? You pick the right one first. Then will it be able to pick this right one? Obviously, since this right one is already occupied, so it will not be able to pick this right one, right? I mean, obviously there are two cases. Either it can pick before this philosopher. So let's suppose this is philosopher number 1, 2, 3, 4, 5. So 5 can pick this fork before 4, then it is okay. But another case is 4 is picking before 5. So let's suppose 4 is picking before 5. In this case 5 will not be able to pick, because to 5 I am saying you pick the right one first instead of left one, or maybe left or right does not matter. I mean, instead of this one you pick the let's call it right or left. Okay, maybe I will be calling it left, and these are the right. So I will say that okay, you pick the left one first. Then this philosopher will say, since it is occupied I cannot pick it, so I will say okay, you should wait. Then if you cannot pick, you should wait. Then so now this fork is empty, so that is why this processor or this philosopher can use this fork and can run, or maybe can eat, right? And then once it finish eating, it will leave up both of the resources, and then this processor will be using these two resources. It will finish, then this fork will be free, and then this processor will be doing its job, and then this fork will be free. Like that you will be avoiding the deadlock, right? So there is a way to avoid deadlock. It's not like there is no way to avoid deadlock, and one of the ways that you introduce asymmetry in this particular case. So let's just see which one is the correct answer. What they are saying, a solution to dynamic philosopher problem which avoids the deadlock is to ensure that all philosopher pick up the left fork before the right fork. So this is a symmetric condition, right? I mean, everyone is picking left, 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 or maybe everyone is picking right, right, right. So in these two cases deadlock might arise, right? There may be deadlock. Okay, and C is saying ensure that one particular philosopher picks up the left fork before the right fork. So they're saying one particular philosopher, I'm saying pick up the left before the right, and for all of them I'm saying you go for the right before the left. So basically here I'm introducing asymmetry, so that's why C is the correct answer. So it will never lead to deadlock, right? Never lead to deadlock. I hope that is fine to everyone. Let me know if you understood this. So that's very nice question, very easy question, but you have to understand the mechanism behind it, like how we are avoiding the deadlock, right? So that's how you can avoid deadlock. Okay, let's go to next problem. What this problem is saying, they are saying that there are 1 to 9 processors which is defined, the code is defined like that, and the code for p10 is identical except it uses v mutex in place of p mutex. Okay, so they are saying that there are 10 not processor, there are 10 process, and all of them are using same code except p10. And in p10 what do I have? In p10 instead of this p mutex I do have v mutex here. That's what they are saying, which means this is the code for p10 and this is the code for p1 to 9, right? That's what they are saying. Now the code for p10 is identical. What is the largest number of processes that can be inside the critical section at any moment? So they are saying what is the largest number of processes that can be inside the critical section, and this is the critical section. And mutex, generally they should be giving that what is this mutex. I mean, if it is not given, then mutex is generally treated as binary semaphore. Okay, this variable is very special, and that is reserved for the binary semaphore generally. Okay, so can you tell me what is the largest number of processes can be in the critical section? See, let's suppose it is initialized to 1, then you can enter p1 and that will be in the critical section. But at the same time, when p1 is in the critical section, you can increment the value using the p10. Using the p10 you increment this v mutex using this v mutex, and then you can let enter p2 also. And if inside p2 is there, you can increment using this vmutex again, and then you can let enter p3. In fact, you can execute this code whenever you want to, right? You can execute this p10 whenever you want to. So that is why you can let all the processor enter at the processes enter at the same time, and also you can enter using P10 also. So all 10 you can enter, right? So answer is none. Why? Because 10 is not in the option, so that's why answer is none. Yes, yes, Kartikan, that is correct. Okay, so I hope you understood. Now let's move to the next problem. What this problem is saying, that consider the following solution to producer consumer problem using a buffer of size 1. Assume that initial value of count is 0. Okay. Also assume that testing of count and assignment to the count are or are atomic operations. So they are saying that producer consumer code is given to you and there is a buffer of size 1. Okay. So let me just go to the next page. This is the code for producer and consumer, and then let's just keep it side by side. This is the code for consumer, right? And then what they are saying, show that that in this solution it is possible that both processor and processors are sleeping at the same time. So they are saying there could be deadlock or something. I mean, can you show me execution where both the processors, producer and consumer, are sleeping at the same time? Right? So that's what they're asking. Let's just see if we can do it. Okay. So I mean, you can preempt at any point in time. Maybe you can preempt it here. It is a pseudo code. So after this you can preempt here. After this, if a statement you can print, after this line you can preempt. You can preempt anywhere, right? So suppose that first producer comes and count value is initially what is given? Okay, 0. Count is 0. So suppose producer comes, since it is 0, so that's why it will place an item in the buffer, and then it will set the count to 1. And then if the consumer is sleeping, it will wake it up. And then it can again come. If count is 1, it will sleep. So now there is one item in the buffer and actually it is sleeping, right? So let's suppose that producer is sleeping. Now at the same time, can you ask this consumer to sleep? Right? Since count is 1, it will not sleep, right? It will sleep if count is 0 only, it will sleep if count is 1 only. So that's the problem. It will remove the item, it will make the count 0, it will wake up the producer, right? So okay, so now it is waking up the producer, and then count is again 0. So it's the initial condition that we have. Both are woke up and count is initially 0. So I think it will not help us, I mean, this kind of execution, right? So basically I want both the processors to sleep at the same time, but the problem is that this producer will sleep when count is 1 and consumer will sleep when count is 0. Let me know if it is possible to make them sleep at the same time. Maybe what you can do, maybe let me just tell you one of the possible execution. Let's suppose that initially count is 0. Okay, you execute this count 0, you don't go to sleep. Okay, basically I just want to waste one of the wake up of this wake up consumer I want to waste, or maybe wake up producer I want to waste. Okay, so suppose that you don't sleep, you are still here, right? You are here. Now there is a preemption, and because of that it will place the item, it will make the count 1, and it will wake up the consumer. But since the consumer is not sleeping, it will not wake up, right? So consumer is here and producer has made count to be 1. Since the count is 1, producer will go to sleep definitely, but the consumer, when the consumer execution begins, it will also go to sleep. So that's why you can make both the processors sleep at the same time, right? I hope that is fine. So one idea is that you execute this statement and then you preempt here, because I want this wake up consumer to get lost or get wasted. Similarly, another idea could be, maybe you can say, that instead of preempting it here, maybe I can say that okay, initially count is 0, but let's just make this count 1. Okay, count is 1, and then it has placed one item, and then it is coming back. Since the count is 1, that's why it will go to sleep, but don't let it sleep, right? Just preempt here. Now producer is here and count is 1. Now it will make this count 0, and then it will come here again and then count 0. Since count is 0, it will get sleep, right? So consumer will sleep and producer is here. And then when producer execution begins, it will also go to sleep. So basically, this wake up producer has been wasted because the producer was not sleeping when the wake up producer got called. So either you waste this wake up producer or you waste this wake up consumer, right? In both the cases, you can have a deadlock. Right. So in these kind of questions, you have to, you have to try some of the preemptions, that where to preempt, where not to preempt, right? Okay. So Deepak has written this answer. Run the consumer first, test if now run the producer. No. So okay. So there is one of the possible execution. There Deepak has shown that okay, it is possible that both can sleep at the same time. I think Deepak is talking about run the consumer process first. Maybe he is talking about this kind of thing where he is wasting this wake up consumer. Maybe you can do this also. You can run the producer also first, and then you can waste the wake up producer. Right? You can do any one of them. Okay. So what I'm saying here, that you can preempt anywhere, and then you don't let it sleep. You just preempt just before the sleep. So in this case, what will happen? Whenever consumer is executing, then wake up producer will get wasted because no one is sleeping. So that is why now again the consumer comes. Since the count is 0, it will go to sleep, and then producer comes, it will also go to sleep. Okay. So maybe you can solve this question later if there is any other doubt. Now let's solve this question. In this question, what they are asking is that so in this question they are saying let M0 to M4 be mutex, and specifically they mentioned that these are the binary semaphore, and P0 to P4 are the processes, right? P0 to P4 are the processes that we have. Okay, and then maybe I hope my screen is visible. Let me just make it minimized. And then they are saying that suppose each of this PI is executing following code, then this code can lead to. Can anyone answer this question? This code can lead to what? Will it lead to deadlock or not? Have you seen such kind of implementation? This is not a very good implementation. Have you seen such kind of implementation? This is a circular weight, right? This is a dynamic philosopher problem where I am saying that okay, mi, which means this fork I, then fork I plus 1. To everyone I am saying go to your I and then I plus 1, right? Maybe to your left, and then the first go to left only. First go to left. So everyone will do what? Everyone will say that okay, wait mi. Everyone will get preempted here. Let's suppose everyone is getting preempted after this point in time. Then whenever next process is coming, it will get it has to wait for some other process to leave. So this is a circular wait. Circular weight, just like one problem that we have just discussed, right? And we have discussed in the detail, which is a dynamic philosopher problem, right? This problem, just like this problem, it is also having a circular weight. Right? Okay. So I hope you understood. Now let's just move further. Yeah. So they are also saying it's a circular weight. So what they're asking in this question is that fill in the boxes below to get a solution for the reader writer problem. So this is a reader writer problem using a single binary semaphore. Okay, that is interesting that they are saying just use a single binary semaphore to solve this, and busy waiting write in the boxes number. So there are some boxes which is number 1, number 2 and number 3. So there are 3 boxes. In these 3 boxes we have to write something such that it is a correct implementation of the reader writer problem. Now they are saying that we do it using the binary semaphore. Okay, so I mean, why it is making any difference? Because the reader writer problem is generally solved by the counting semaphore, right? But here they want to use the binary semaphore. So let's suppose this signal and wait mutex. So this mutex, yeah, mutex they have given that to a binary semaphore initialized to 1, right? So here I either need to write signal or I need to write the wait. So tell me, in this first Should I be writing wait mutex or should I be writing signal mutex? Okay. Similarly here, what should I be writing? Similarly at this box, what should I be writing? So in these three boxes, I need to write. In these three boxes, right? In these three boxes, we need to write. Now let's just see how to solve this problem. So there are two types of semaphore. One is binary and one is counting semaphore. Now, in case of binary semaphore, it does not count basically. I mean, you do not have any count implicit. But in case of counting semaphore, okay, counting semaphore. Count is implicit. So I can implement, suppose that I want to implement the counting semaphore using the binary semaphore, right? So what I need to do, if I want to implement the counting semaphore using binary semaphore, so binary semaphore only provides the semaphore facility, right? Binary semaphore whatever the functionality is provided by the semaphore, it just provides this, right? Let me call it mutual exclusion. It does not actually provide the count. So binary semaphore plus, let's suppose if I explicitly use one integer or one count variable, then probably I can implement this counting semaphore. So using binary semaphore and then one count variable, I can probably implement this counting semaphore. Okay, that's what we will try to do here. Now let's just see that how we can achieve this. So as you notice here, this R and W are explicitly two count variables, right? Which means if you see the reader writer program, there if you are using the counting semaphore, then at that time we do not need to use the explicit variable which is R and W, right? I mean, I do not need two integers, but here I will be needing some integers. Reason being is that I am using the binary semaphore here, so that's why I will be needing some integers, because these are just explicitly count variable that I am having, right? Let me know if you are able to understand what I am trying to explain. Okay. Okay, so I hope you understood, right? Now let's just try to implement. Now what they are saying is that this wait w equal 0, and then this is wait mutex, and this wait mutex should be having the corresponding signal, right? Otherwise how you will be doing this operation? So basically this wait mutex should be having the corresponding signal. Like why I might be having the wait mutex? Maybe I am incrementing this r, right? Just to increment this r, I need to provide some security. So because to prevent the race condition. Now this signal mutex, like at this one I can write the signal mutex, but should I be writing it at 1 or should I be writing at 2? That's the question. See, definitely, I mean, this wait mutex is outside my if condition. So definitely, if I write it here, if I write the signal mutex here, right, signal mutex here, then it seems fine. I mean, you are doing wait mutex, and then if you're incrementing it, then it is basically this whole thing is within the security, right? Is within the security. But what if you are not even executing this if statement? What if you are not at all executing this if statement? Then what is the corresponding signal for this wait? If you are not at all executing this if statement, then there should be the corresponding signal for this wait, right? So what I'm trying to say is that this there is a wait mutex. I might have provided this like security to this r equal to r plus 1, but for that I need corresponding signal mutex also. Now the question is that should I be putting the signal mutex at 1 or 2? The answer is that we have to put at the both places. Okay, why we need to put at both places? Because if I just put at one of the place, then it is not sufficient because of some reason or other. Let's suppose if you put only at one, then what if the if statement at all not get executed? Then this is wait mutex and there is no corresponding signal. So what will happen, that you will not even be able to execute this wait mutex, right? Like lagatar 2 wait mutex you cannot execute. So there must be corresponding signal mutex. So that's why I need to put it else statement. Similarly, I need to put it if statement also. What if you do not execute the else statement, right? I mean, you come to this if statement, then here you will be needing some signal, corresponding signal. So that's why there will be signal at if condition, at else condition also, because you will be executing one of them, not I mean both of them at a time, right? So at both the places I might be needing the wait, sorry, signal, right? I hope you understood. Now let's just come to this here. What I should be writing? Should I be writing the wait mutex or signal mutex? What do you think? See, this is inside the wait. Okay, I think this is already inside the wait and signal. So I should be writing, I mean, this should be clear from the options. I need to check that what I should be writing. So since it is a writer, let's just read the problem definition. They are saying, okay, okay, in the problem they have not specified anything. So let's just check what I should be writing here. I think I should be writing something like, if there is already one reader or maybe already some writer is there, then maybe I should be looping, right? It is saying loop, it is saying loop. So when I should be looping, what do you think? When I should be looping? There is at least one reader is already there, right? Or maybe some writer. So here, I mean, it should be clear from the options, but it was a subjective question in 2000. So you can say that if there is at least one reader or maybe at least one writer, okay, w not equal to 0, maybe w greater than 0, you can write anything. Which means there is at least one reader or at least one writer, then I should be looping, right? So here you will be writing, okay, if r is greater than 0 or w is greater than 0, at least one reader or at least one writer, then you should be looping, since this is a loop. Cool. So let's just go to the B part of this. What they're saying, can the above solution lead to starvation of writers? Tell me, can this solution lead to starvation of writers? Which means writers are not able to enter in the critical section. Is this possible? Let's just check. Okay, this is the problem, and then they are saying, is it possible that I might not, as a writer, I might not be able to even enter in the critical section. Okay. So here it is signal mutex. It is also signal mutex, and if I am saying here, if r is greater than 0, if r is greater than 0 or w is greater than 0, let's just check. Can r always be greater than 0? If r is always greater than 0, then it will be looping, right? So let's just check. If r is initially 0, I will come here, and if w is 0, let's suppose w is not 0, then I will not increment it. Okay, initially w is 0, so I will say, okay, there is one reader, and then I will ask the reader to go out, right? But it might be possible there are always like multiple readers are always there, right? I mean, r is always greater than 0. It is very much possible that r is always greater than 0. Since if r is always greater than 0, that's why you might be always looping, because I'm not limiting the limiting this number of readers. I mean, you can go out, but you can go again in. So there is at least one reader always in the critical section. This is very much possible to have. This is very much possible to have at least one reader in critical section, right? So that's why it might always loop. So case is asking, how can the reader process be blocked if other process is writing in the reader code? I'm not saying it is locked. When did I say it is locked? Placing signal at 2. Placing signal at 2 doesn't mean it is locked or something. There is no loop. Okay, there is this signal you are asking. So what you are saying, that if you are putting the signal here, then this is within the else statement. So okay, so it means that w is greater than 0, which means there is a writer, right? If there is a writer, then obviously you need to loop. So like if you are in the else statement, then there is a writer. Okay, so writer has a different code and reader has a different code. If there are there is a writer in the critical section, then the reader will say that okay, I need to lock, which means the else part is saying that there is a writer, right? So else part is saying there is a writer. If there is no writer, then you just increment the reader count, which is r equal to r plus 1. Okay. Okay. So answer is yes, writers can star. There can be a scenario where the writer try to enter, it finds the some reader is always there, and it keep on waiting, right? Okay, cool. Now let's solve this question. This question has been asked in GATE 2002. So what they're saying, the following solution to the single producer, single consumer uses the semaphore for the synchronization. So this is single producer, single consumer problem. Okay, let me just copy this problem on the next page. Right. So this problem is single producer, single consumer. Now what they're asking is that complete the dotted part in the above solution. I mean, you need to complete with these kind of statements where empty, p empty, p full, something like this, right? I mean, in the dotted part, you need to write somewhere p empty, somewhere p full, something like this. So let me do one thing. Since this is a producer consumer code, so let me write it side by side. These are the common variables that we are using. This is the producer that we have, right? Let me write it on the one side and let me write this consumer on another side. Okay, now let's just check what they are doing. So this is void producer, and then what they are saying, that fill something here, fill something here, something like this, right? Now tell me, this buffer size is okay. Now tell me, this b full means what? I mean, initially it is 0. So what do you think in case of producer consumer? What do you think this b full could be? This is number of empty locations, number of full locations, or what it is? Number of items. Can I say it is number of items? It is basically a semaphore which is actually counting semaphore, and it is telling me number of items, right? I mean, it is basically counting also. It is telling me number of items, right? Is this fine to everyone? Initially the number of items are 0. Initially I can say number of available slots, number of empty locations basically is basically full. I mean, is buffer size, number of empty locations. This might be telling me number of empty locations, right? So this is the meaning of these two variables that we have currently. Now let's just see that how to proceed with this question. Now what they are saying, produce one item and then P1, then put the item into the buffer, right? Okay, and then they are saying first, which means this is just a location that they're denoting, let's not worry about it. And then they're saying produce an item. Okay, tell me, once you produce an item, what you should be doing? You should be incrementing the number of items or number of empty locations. You will be incrementing the number of items, you will be decrementing number of empty locations, right? So you will say you will be incrementing number of items. That's why p of b full should be there. B full should be there. It is fine to everyone. If you are producing, then you will be having like, let's just increment number of items, or should be empty, tell me. Okay, this is p means decrementing. So you will be decrementing what? Number of empty locations. So number of empty locations you need to decrement. That is why it will be b of empty, right? B empty, because you need to decrement it. And similarly you need to increment number of full locations, so b full, right? Once you produce an item, then you need to decrement empty location, increment the full location. Similarly here also you do the same thing. Like when you want to consume, at that time what you will be checking, whether the number of items, you will be basically consuming the items, so you will be decrementing the number of items, which means you will say p of number of items, which is b full, and you will be incrementing number of empty locations, so b of what is the empty location? B empty. So that's how you can solve this problem. Now, why I'm writing P here and why I'm not, since I need to do two tasks here. In the producer, I need to do two tasks, decrement, something increment, right? Similarly, in the consumer also, I need to do two tasks, something decrement, something increment. But why I'm not reversing the roles, which means why I'm not saying P and V should be actioned, why I'm just saying that P and then V only? Any idea about it? Because see, whenever I'm coming at that time, I should be checking, like whenever I'm as a producer I'm coming at that time, I should be checking if this is already if it is already full, which means BMT is telling you number of empty locations, right? If number of empty locations is, let's suppose, 0, number of empty locations, let's suppose 0, then I should not I should not do all of this, right? If number of empty locations are 0, which means that I cannot place the item anywhere. So that's why I need to check first whether the number of empty locations is 0 or not. So that's why always in the correct implementation I have P and then V, right? Similarly P and then V. Whenever I'm as a consumer I'm coming, then I need to check number of items, right? If it is already 0, I should not proceed further. Okay, so this is the answer. See, empty, full, full, empty, empty, full, full, empty, right? Now there is a B part of this question which is saying something like this. Maybe okay, which is saying that using another semaphore variable, insert one line statement each immediately after P1, immediately before P2, which means immediately after P1 here, immediately before P2 here, and immediately after C1, which means here, immediately before C2, which means here. So they are saying insert 1111 line here, total insert 4 lines, such that so that the program works correctly for multiple producer and multiple consumer. Currently it is for single producer, single consumer. Now they are saying that do something such that it works for multiple producer and multiple consumer, and insert something here. So what you will be inserting? See, currently since I'm incrementing this, since I'm just using a counting semaphore, and if it is multiple things, then it might lead to a race condition, right? So I need to protect this incrementation. I need to protect this with the binary semaphore. So maybe you can have some mutex and you can just write p mutex, b mutex, p mutex, b mutex, right? So maybe something like this. See, here if you can see the solution, it is saying p mutex. You can have just one mutex, or maybe you can have just maybe two mutex. It depends on our requirement. I'm currently using two mutex, probably because I want to say that if the producer is maybe, producer is, let's suppose, producing or maybe incrementing some variable, and then at the same time I can let the consumer also increment or decrement its own variable, right? So maybe it is fine. Since these are actually working with the different variables, which is first and then this is last. Since I do not need the synchronization between first and last, so I can allow it, which means if it is first and first only, then I must be having only mutex, one mutex only. No two mutex is allowed. But if there are first and last, there are two variables, that's why I can say that okay, let's suppose let me work with the mutex 1, mutex 2 here, because mutex 1, mutex 2 allow you for the more concurrency, which means they are saying at the same time you can increment last and at the same time you can increment first also, right? Some producer is incrementing first, some producer consumer is incrementing last, perfectly fine to me. Okay, that is perfectly fine to me. So that is why I'm saying that you can use two mutex, and if you don't want to allow the concurrency between the first and last, which is actually not a good idea, so you can just use one mutex, but that will just limit your to not allow the concurrency. Okay, so I hope that is understood to everyone. Good. Yeah, now let's move further. Now what they are saying, the following program consists of 3 concurrent processes and 3 binary semaphores. Okay, the semaphores are initialized as 1, 0 and 0. So there are 3 semaphore and 3 processes, which are this. How many times will the process P0 print 0? Okay, so that's what they are asking. Maybe I can copy this question. So they are saying how many times you can print the 0. Right? So this is the initialization, and these are the processes that you have. Let's suppose I want to check that how many maximum number of times you can print. So initially this is 1, which means okay, See, this is wait, this is release, this is wait, this is release. Okay. I mean, I just want to understand the mechanism, like how they are actually working. At least, at most. So as you notice one thing here, this p node will run infinite number of times because while true is there, but p1 and p2 you can just use one time. Okay, which means you can increment s node one time on the cost of decrementing s1. You can increment s node to one more time on the cost of decrementing s2. I hope you understood the problem at least, right? So what they are asking, they are saying that p node can run infinity number of times, p1 and p2 will be running just one time. Okay, and then they are saying that how many times you can print this s node. They are strictly saying that you have to start with the s node, which means you cannot start with p1 and p2 because these are the weight. Okay, let's just start with s node. I mean with this, then you will be printing 0. Okay, let me write the values here. This is s naught initially, s1 initially, s2 initially. So initial values are 1, 0 and 0. Let me know if that is fine to everyone. Now what we are doing, we are starting with this s naught, and then because of this weight s naught, it will come to 0, right? And these values are still 0, 0. Okay, I mean I'm not writing it again and again, but this is the latest value that I'm writing here. This is the latest value I'm writing here. This is the latest value I'm writing here. Okay, anyway, so this is currently 0, 0, 0, and now we will print 0. So this is what we are printing here. Print 0. This is what we are printing. And then what you are saying, release s1, which means you will be incrementing it. Right now, you are here, right? I mean, you are here. Now you can increment both. That is a normal human thinking. Or maybe let's just check if there is any benefit of preemption. Suppose I preempt, then at least I can execute this p1. I can execute this p1, and that will make this. What is the benefit of executing this p1? This p1 and p2 I can execute just one time. Okay, that's very important. So that's why I have to be very careful when to execute it. You are getting my point, I hope, right? So you can just execute p1 and p2 one time. So that's why you have to be very careful when to use that execution. And what it is actually doing, it will again make this 0 to 1. That's what they are doing, right? Okay, so maybe let's just use this execution. Okay, which means that after this preemption, you just go here, and then since it is 1, it will make this to 0 and this to 1, right? That's what it is doing. Actually, the s1, 0 or 1 does not matter much, because I will after this preemption, once I use this p1, I will never use this p1 now, right? Okay, now let's suppose I come back here. Now I come back here, I have consumed my p1. Now is it a good idea to consume p2? See, it is never a good idea to consume p2 whenever s2 is s0 is 1. Reason being is that p2 will make it 1. P2 wants to make it 1, but whenever it is 1, then it is not a good idea to consume this p2. I will consume this p2 when only when the s0 is 0. If s0 is not 0, it's not a point to consume this p2 unnecessarily, because it will not do anything. Ultimately, it will just make it from 1 to 1, right? You're getting my point, right? So I will not consume this currently. I will just release this s2, which means make it 1, right? Make it 1. And then, okay, s1, now I do not probably care about the s1, right? Anyway, let's just write it, but yeah, I will make it 1. And then I will again go here. I will wait s0. So because of the wait s0, I will make it to 0, and then this is 0. I will print 0, release s1. Because of the release s1, it will be 1. Actually, s1 now it is release s1 always, but it won't matter to me because the s1 wait I will never execute. So anyway, now release s2. Okay, again you can make it 1 or something, right? But tell me, once you print this 0, right? Once you print this 0, okay, release s1, release s2, it is okay. But tell me, once you print this 0, is it a good idea? Okay, you can do the release s2 maybe, where it is already 1. You can do it again 1, but after it maybe, like, I mean, you are stuck in the wait s node, right? You are stuck in this wait s node. So is it a good idea to call this p2 right away? Yes, it is a good idea, right? Because it will at least let me out. So basically, you can print 3 times, and then this is also over, right? So 0 one time you can print because I initialized to 0. Again you can print 0 because the p1 can make it 1, right? Again you can print 0 because the P2 can make it 1. But now no one, now it is 0, now no one can make it 1. So that's why I cannot print more than 3. So 3 times at most I can print. Let's just see the answer. Exactly 3 times or at most 3 times. So answer currently I'm at the stage where I'm saying at most 3 times. At most 3 times. But I think they are not interested in the at most. They're interested in exactly or at least. So let's just analyze it a bit more, right? So I hope this analysis is clear to everyone that what we are currently doing. So currently, let me know if there is any doubt. What we are currently doing is basically, we are saying that you want to print 0 as many times as possible, let's suppose, then you can print 0 because this S0 is initialized to 1. You can print 0 because P1 can make it 1. You can print 0 because P2 can make it 1, right? So you can print 3 times, at most 3 times you can print. Now let's just check at least how many times I will printing. Okay, so maybe I can go to the next page, right? So at most 3 times. At least means I want to let's suppose this is at least, which means I want to waste this P1 and P2, right? So initially it is the case that S0 is 1, S1 is 0, S2 is 0. Now obviously I have to print at least once, right? I mean it is 1, so I cannot stop it printing. So maybe I have to print at least one time. I have to print at least one time. Now again, now it is 0, right? Now it is 0, yeah. Now the problem is that see, I have to execute this P1 and P2 also. So the problem is that initially these are 0, that is okay. Well, the problem is that I have to, once I do this release or maybe before release, I have to execute them 1 and 1, right? So I cannot keep it 0 forever, which means that I have to update that to 1 because somewhere down the line P1 will get executed. That's the problem, right? But the good thing is that I can execute P1 and P2 just one after another, which means let's suppose this release S1 and release S2 is making 1 and 1, right? And then at this point in time, I'm executing P1, which will make it 1, executing P2, which will make it again 1. So basically I'm wasting this P2, or maybe I'm wasting P1, which means I'm going from 0 to 1 just one time, although I'm executing P1, P2 both. So that is why like it will be 1, and then P1, P2 both are destroyed, and then you will be printing 0 again, and then this will be decremented to 0. Then release S1, release S2 does not matter because both are destroyed, and then once you go back here, then you will be stuck here. So at least 2 times you will be printing, right? At most 3 times, at least 2 times. At least 2 times. Which means you can print in between 2 to 3. Maybe you will be printing 2 zeros, or maybe you will be printing 3 zeros. That's the only answer. At least thrice, no, right? Exactly thrice, okay, at least twice, yes, at least twice you will be doing. So that's why this is the answer. Exactly is never the answer because either you will be doing it 2 times or 3 times. So at least is answer, right? At least or at most could be the answer here because I am having a range. I am not having a fixed number. Sukesh, is this clear to you? Saurabh, Karthikeyan, Jashkaran, is this clear to everyone that how we are solving this question? This question is nice question, like I mean you should be able to solve this question now, right? Okay. Now let's do this question. This question has been asked in GATE 2013, and let's see what they are asking. They are saying a shared variable x is initialized to 0, is operated on by 4 concurrent processes w, x, y, z as follows. Each of the processes w, x, y, w and x reads x from memory, increments 1, store it in the memory and terminates. So basically there are 4 processes w, x, y and z. Each of the processes w and x read, okay, they read x. Let me just write r means I mean read. They read x, increment by 1, which means they increment, let me just write increment I and cr, increment of x by 1, right? and store in the main memory, and then store. So these are the three instructions that they are doing, W and X. So W and X both are doing the same thing, right? Just like this. And then what they are saying, each of the process Y and Z read X from the memory, decrements by 2 and store in the memory. So basically the difference between W, X, Y, Z is that Y and Z are also doing the same thing, but they are actually, instead of increment, they are doing the decrement, and that to 2 times. Okay, they are doing the decrement that to 2 times. Let me write decrement 2, right? Each process before reading X invokes P operation. So before reading X, each process, so they are saying each process invokes P operation on the counting semaphore S. Okay, so they are using the counting semaphore. Let me go to the next page. They are saying that each process invokes the P operation on S, right? P operation on S, each of the process is doing the same thing, and where S is a counting semaphore, right? And V operation on the semaphore after storing the value in the main memory. So V operation, V of S after store. So each process is almost identical, where W and X are identical, and now Y and Z are also identical. Now semaphore S is initialized to 2. What is the maximum possible value of X after all the processes complete execution, right? So S has been initialized to 2. Now what they are asking, what is the maximum possible value of X after all the processes complete execution? So S is 2 means what? At a time, since it is a counting semaphore, it is 2 means what? At a time, you are allowing at most 2 processes in the critical section, right? So what could be the maximum value? See, to have the maximum value, what I want to do, I want to nullify the effect of Y, I want to nullify the effect of Z. Can I do it? Maybe very easily I can do it, right? I mean, you read X initially, okay? So, yeah. So, what is the value of X initially? A shared variable X is initialized to 0. So, you read it 0. You want to have the maximum possible value, right? You increment it and do not store. So, here the X is currently 1. And then do what? You just, execute this Y completely, which means you execute Y? Yes, you can definitely execute Y. How? Because S is saying that you can allow, since it is a counting semaphore, it means that you can allow 2 processes at a time. W is currently in the critical section. Can you allow Y? Yes, you can allow. Matlab, 2 processes you can definitely allow. So if you allow Y will be getting destroyed, because it is just one time execution, no while loop forever, right? So it will get destroyed. I mean, destroyed means it will increment the X value, and then decrement the X value, which is -2 or something. But let's not worry about it, because it is anyway going to overwrite, right? Similarly, you can destroy Y. Similarly, you can destroy Z. So you now overwrite it, which means now it will be 1, and then it will be again 1, 1 plus 1, 2, right? So basically you can just have these increments, and then you can just nullify this Y and Z. So that is why 2 is the correct answer, right? Let me know if it is clear to everyone. So D is the correct answer, right? So 2 is the maximum possible value. Okay. Now let's solve this question. This is very nice question. What they are saying, a certain computation generates two arrays A and B such that AI equal to Fi, right? So AI is equal to Fi. F might be some function. So maybe, okay. So here we have a code for process X and process Y. Let me just copy these two code for process X and process Y and go to the next page. Okay. So let's do this question. Now they are saying that there are two processes. Here Bi equal to G of AI. Now interestingly, this B is depending on G, right? So so on A. So basically AI is not depending on this B, but this B is depending on A, which means that there is an array A which may be looking something like this, right? There is an array A which is, let's suppose, looking something like this, and there is an array B which is looking, let's suppose, something like this. Now what they're saying, if you want to compute any of the index of this AI, okay, then you can compute it, you can compute. But if you want to compute any of this index, then you have to make sure that corresponding this index has been computed or not, because then only you can compute it. Now tell me, can you compute it before computing this value? Obviously no, right? So you cannot compute, because any of the B index before computing corresponding A index. That's what they are saying. That's the dependence that they have, right? Okay, process X and Y compute A, and by compute the array B. The processes employ two binary semaphore R and S, both are initialized to 0. See, there are two binary semaphore R and S. Okay, now currently they have not written the what is this entry and exit, so that's what they're asking. Like, what should be the entry and exit code? The structure of the process following. Which of the following represents the correct implementation of entry exit? So basically, I want to have the correct implementation of entry exit. Is the question clear to everyone? Let me just tell you what this option A is saying, maybe, and then you can understand the question more. So basically, they are saying that there is an implementation of process X is doing something, process Y is doing something, but or this process X is, whatever it is doing, it can do independently, but process Y is depending on process X. I mean, once I have to compute it, then only I can compute B. That's the only limitation. Now what should be this entry and exit as? What should I be writing here? Can I write this PRVS here, right, instead of this exit? Can I write PSVR here instead of this entry, such that it works smoothly? Now as you notice here one thing, that this process will run n time. There is no while infinite, right? This will run n time, this will also run n time. Now suppose I am writing PR and VS, and what is this R and S? R and S are two binary semaphore, right? Binary semaphore, which is providing the mutual exclusion basically, right? Initialized to 0. So suppose if I am writing PR, okay, let's suppose, okay, let's understand this option A. Suppose if I am writing PR and VS here, and suppose I am writing PS and VR here, will it work for me or not? Let's just check. Okay, just a second. Tell me. See, this is PR, it will get stuck. This is PS, both will get stuck. So there is no point in writing P and P at front, right? So that is for sure that there is no point in writing P and P. So since both are P, so that is why both will get stuck. That is why, like, the P and P is, I don't think it is a good idea. So that is why like maybe I need to look up for the other options. So the option is wrong. Reason being is that this process will get stuck after, I mean, this exit statement is obviously not there, because I have replaced this exit with the corresponding code, right? So I hope you're getting my point. So this exit and entry, these two codes are not there, because I have replaced it with the option A. So this is the current code, and I'm saying that this PR, if I'm computing this, let's suppose for I equal to 0, it will run for I equal to 0 till I equal to n minus 1 or something. So it will run n times. So it will run for I equal to 0, and then it will compute this AI. It will compute this AI. Then it will do P of R, which means it will get stuck, no problem, but it will also get stuck, right? So since both of them are stuck, so that's why A is not a good option. Now let's just figure out other options, right? So A is not a good option. Let's just see what could be the other option. Can B be the answer? Let's just see this. Okay. Okay. B is saying VRVS. B is saying something like this. Maybe I can replace. V is saying VRVS here, and V is saying PRPS here. Okay. So you understood this question, right? I mean, what this question is asking? This question is asking that which of the following basically will give you the correct execution. I mean, everything should work very smoothly. That's what this question is asking. Now, if this is VRVS and this is PRPS, then will it work? it will say that okay, let's just I mean, anyway you have to execute this first, and then it will say that okay, let's just do this vs, both are 1 and then both are 0. I don't know why, if we have to use it like that, then why we are using two variables first of all, right? Anyway, but if both are 0, it will get executed, and then you will run this process I again. Let's suppose, I mean, now because you cannot run this again, I mean the process by you cannot run because the PR will get stuck, right? So is this working fine? Tell me. I mean, you run one step this, you can definitely run one step this, then you run one step this, you can definitely run one step this. I mean, it seems like it is fine, right? I mean, one step seems fine, but that's like a very normal execution. What if it doesn't run in that way, which means that you need to check all the possibility, and all the possibility things should be smooth. Can you run process by multiple times? Obviously no, because there's a p, so that's why you cannot compute this b, and I mean that is fine, that is what we want. But can you run x multiple times? Yes, you can run x multiple times, right? So if you run x multiple times, then will it be a program? Let's just see. If you're running x multiple times, let's suppose you're running it n times, and then all of these entries are filled. Now you try to compute this b, right? You try to compute this b. The thing is that if it is running n time, then after n time it won't run, which means you will destroy this. You will say that okay, I'm not going to run this now. Now try this with processor C, this process by. Now can you run it one time? Definitely one entry you can compute, but after it will get stuck in P, and no one is there to make it one, because you have just destroyed it, because you have said okay, I run it n times, and after n time I'm not going to run it, right? So if you do in that way, if you're putting v here and p here, then the problem with this is that this v are getting unuseful. Basically this v are getting wasteful. If you're doing lagatar, if you're doing 2v, that is not a good idea, right? It means that you are wasting this v, and you have wasted all the v, just last v is useful, and then you are doing this process y, right? So that is why I mean, this idea, this b is not a good option. Reason being is that you can compute this a, and then after it, if you want to compute this b, then it is not possible. Only you can compute one of the entry, but after it you cannot compute other entries. Let me know if there is any doubt in this, like why b is not the correct option, because in this case you cannot compute this like array b completely, right? Okay, now let's just see if maybe some other option. So okay, I don't want to have the answer, I don't want to execute the answer. So what is the answer here currently? Okay, I think answer is C. So let's just first try with D. Will this D work or not? Have you understood the question at least? Okay. So let's just check if this D will work or not. So D is saying VRPS, right? V is saying VRPS, and then VSPR. This is what it is saying. Let's just check, will this work? So basically my idea is that I don't want to waste any of the V, right? Tell me, can you waste any V here? I mean, waste in the sense, whenever I'm doing one, I don't want to do two V's. If I can do two V's consecutively, it will be a problem to me, right? Reason being is that it will say that okay, I am done. See, I don't want to do two V's consecutively, because corresponding P is here, right? Corresponding P is here. If corresponding P is here and I do this two times consecutively, then this P will be just getting one V, and one of the V will get wasted. Now tell me, can you do two V's consecutively? Both of them are R and S, both are initialized to 0. I think you can do it, right? If you do it, then R will be 1, and okay, that's interesting. Let's just check if you can do it. Can you do this two V's consecutively without doing this P of R even once, right? So which means I want to check, can I do VR, this VR, and then again VR, maybe in between basically this, there should not be PR and then PR. If this kind of execution is there, then I will say that it might lead to a problem. Let's just check if this, first of all let's just check if this kind of execution is there or not, then we will check if this is leading to a problem or not. So you see R and S both are initialized to 0 0, then VR will make it 1, then PS, and then that's why it will get stuck here. Then you might run this Y because it is stuck, then VS it will make it 1. Now you are currently here. Now you can definitely execute this PR, but that's not what I want to do. I don't want to execute PR. I want to execute PR. I mean, I have just executed VR. See, that was the process. I executed VR. I stuck at PS, right? I'm currently stuck. And then I executed VS. And instead of executing PR, I want to check whether I can execute this VR one more time. And in between these two VR, I don't want to have any PR. Let's just check, which means that currently the values of the semaphore are here, and this process X is getting stuck here, and at Y I am here, and let's just preempt it here at this point right away. Let's just preempt it. Okay, if you preempt it at this point right away, then can you execute, so this stuck will get over, right? I mean, because PS will get executed and then this will be 0, right? So you will be out of the loop. And then since you have executed it one time, so you must have computed A of 0, one of the entry you must have computed earlier, and then you compute one more time, and then VR will say that okay, this from 1 it is again 1, and then it will get stuck, right? So what is happening here? Here you are executing, you are actually computing two items of A, and then none of the B item has been computed yet, right? None of the B item has been computed. Okay, don't worry, just go step by step. I want to clarify things very slowly, so that's why it might take some time, because this is very nice question, right? So tell me if this kind of execution is fine, that you are executing this VR two times without even executing PR one time. So if you're doing so, then you have not computed any of the entry of this B, and then you will be executing this PR, it will make it 0, then VI. So basically you will be computing this, right? So now what's going to happen? You have computed these two entries, but just one entry of this. Now since both are zeros, and then maybe like, I mean, it does not matter, maybe you can run this P or X, whatever you do, but the thing is that you are at your initial step. Initially you started with 0 0, now also 0 0, so that's why you are at your initial step, right? And currently you do have two entries in A and only one entry in B, which means if you just do exact same thing again, then you will be having two entries, because this is just an initial condition. You will be having just one entry in this, and then similarly you keep on doing it, you will be having two here, you will be having just one here. You keep on doing it, you will be having two here, you will be having just one here. And then this, since this length is n, this length is also n, and then once this is n, you will be having just n by 2 entries here. And then once it is full, right, this for loop will get over. It will say that okay, my working is now over, I don't want to run again. Now here in this Y, you will not be able to fill this, because this PR will say that there is no one that can make it one, right? So that's why there will just n entries in A and n by 2 entries in B. So that will be a problem to us. You're getting my point? So basically what we wanted to check, can is it possible to waste one of the V? Since it is possible to waste one of the V, that will lead to this kind of situation. So that's why D is not the correct answer, right? Is this fine to everyone? Okay, so I will say C is the correct answer, right? Let's just analyze this C also. So this is the option D, right? This is the option B, this is the option A, and after analyzing these three, let's just analyze C. So let me remove all of this. Okay. Now let's just check what the C option is saying. This is saying that here PS and VR, right? Cool. So this is having PSVR, this is having VSPR. So now let's just check if I am getting the correct answer in case of C. So what I want to check whether I'm wasting one of the V, right? So can you waste one of the V, or this is strict alternation? Let's just check. Since both of the values S and R both are initialized to 0, you will get stuck here, and then you will so S and R, okay, both are initialized to 0. So you will get stuck here after computing one of the value. Then you are currently waiting here because this is P, and then VS will make it 1. Then tell me, can you execute VS again? PR, you will get stuck here, right? You will get stuck here. Now you have to execute this only, right? I mean, what I want to check between two VS, I don't want to have, let's suppose, PS, okay? So let's just check if two BS are possible, or maybe two VR are possible without having PS, or maybe two BS are possible without having PS, right? So initially it will get stuck here, and then you will come here, you will make it 1, you will get stuck here because it is PR. Now VS I have executed one time, right? And then I want to check without executing this PS, can I execute it one more time? So VR, VR will, I mean, you will come here, and then this PS will say that okay, this will make it again 0, this PS will make it again 0, right? So I think there is no possibility. I mean, see, the execution flow that we are doing, let me just go step by step how we are following. See what we are doing, we are saying initially S and R both are 0, right? Okay. Now you executed this PS, I mean, you are stuck here, but anyway, that is fine. So you want to execute, you got stuck here, like, I mean, half of the PS is just executed, you just got stuck, and then you are currently here. I mean, you will be executing it again definitely because you are stuck, right? And then VR will make it 1. Now I've executed one time VR, and now I want to check whether I can execute it one more time without introducing PR. Okay, that's what I want to check. Now you go here, uh, sorry, you got stuck here, I'm really sorry, you got stuck here, and then you go here, then VS, right? So VS, which means you will make it 1. So I have executed one time VS, and then PR, right? So I mean, maybe you can unpause this, but I don't want to unpause this, I don't want to resume this. Maybe let's just check if I can do VS 2 times without using this PS. So PR, which means you will get stuck here. Now you come here again, you have to execute this PS. There is no chance that you can execute 2 BS 2 times, right? So you have to execute this PS. So that is why 2 BS are not possible like consecutively. That is why for every BS there is a PS, for every PS there is a VS. So that is why you will be computing one item of A and then corresponding item of B, one item of A, corresponding item of B, right? So that's why this option is a correct option. Hence, C is the correct option and all other options are wrong option. That's very nice question, and maybe with one more time of practice you can understand this question, right? Okay. So I think it is enough for today, and there is one more problem, but it is not too good problem. So I mean, you can solve this problem as a homework, right? Cool. So thank you everyone. Thanks for joining in. And then tomorrow, I think we will not be having class, but whenever we will be having class, we will be starting the memory management now, right? Okay. So we have covered in the semaphore, we have covered many problems, and in general in the synchronization, we have covered these type of problems where the mutual exclusion, progress bounded waiting is being asked. We have covered binary semaphore and counting semaphore, right? Okay. And even in one of the problem, like we have told that how to implement the counting semaphore using the binary semaphore, which means you need to explicitly use one of the integer variable, right? Maybe R or W or something like this.